Hello everyone and welcome back to our course on process planning and cost estimation. So in this session we are expanding our focus onto the primary elements of cost, specifically exploring material cost, labor cost and expenses. We will break down how these categories operate and solve a variety of practical engineering problems involving material weight and cost estimation. Let's jump in. Introduction to cost elements. So to begin, cost is simply the monetary value of resources sacrificed to manufacture goods or deliver services. So we classify the total cost into three foundational elements: material cost, labor cost and expenses. Let's look first at the material cost, which is the expense of raw components going onto the production. This splits into two clear areas: direct material cost and indirect material cost. So coming to the direct material cost, these are raw materials that physically become part of the final product, such as steel used to stamp an automobile chassis, timber for a desk or cotton for textiles. Next, the indirect material cost. These are materials consumed during the process that do not end up in the final product itself, such as machinery, lubricants, cutting fluids or basic workshop tools. So these are categorized under factory overheads. Then comes the labor cost and expenses. So labor cost comprises all wages, salaries and benefits paid out to the personnel, and direct labor refers to the wages paid directly to the workers actively transforming the product, like machine operations or assembly line technicians. So indirect labor conversely goes to essential support staff who aren't directly manufacturing the items, such as shop floor supervisors, maintenance crews and factory security personnel. Finally, the expenses include all other operational costs outside of material and labor. Direct expenses are costs uniquely tied to a specific project, such as renting a special 5-axis machine tool for a customized client order. So indirect expenses are broader operational requirements not tied to a single unit, such as a facility rent, factory electricity bills and insurance premiums. Coming to the analysis of the overhead expenses, let's summarize on how these indirect expenses group together into what we call as overheads. They fall into three main management buckets. Factory expenses. These are indirect production costs like shop floor, lighting, equipment, maintenance and machine depreciation. Administrative expenses. So these are costs associated with general business management, including administrative staff salaries, office rent and corporate legal expenses. Then selling and distribution expenses. These focus on the market pipeline. Selling expenses cover advertising, sales commissions and promotions, while distribution expenses manage physical logistics like product packaging, warehousing and transport. Now we will go with an example for determining the material cost. So now let's apply these concepts to a practical workshop problem. Take a look at the multi-stepped shaft displayed in this isometric view. So all the dimensions are given in millimeter. Our objective is to determine the total weight of the mild steel required to produce this workpiece, given a material density of 2.681 grams per cubic centimeter. Once we have that weight, we need to calculate the total material cost if the market rate is balanced at 100 rupees per kilogram. To find the total volume, we calculate the individual volume of each distinct segment of the shaft. Cylindrical segment A has a 22 mm diameter and a length of 35 mm. Using the formula volume of A, that is pi by 4 d square L, we can calculate its volume as 13304.64 millimeter cube. Similarly, for segment B, since it is also cylindrical component, we can calculate the volume of B as 29486.99, and the volume of C which is a square flange measuring 32 by 32 with a thickness of 15 mm. Using length times width times height, its volume is calculated like this. Okay, length into breadth into height, that is 15360 millimeter cube. And similarly, volume of D, since it is a cylindrical component, we can calculate taking the diameter as 20 and the length as 50, we can calculate the volume as 15707.96 millimeter cube. Note that our density is 2.681 gram per centimeter cube, that which converts cleanly to 2681 kg per meter cube. Okay, the unit cost is given as 100 per kg. So now summing up all these things, all these volumes together, we can get the total volume as 73859.59 into 10 power minus 9 meter cube. Okay, so why we are converting this into meter is because the weight of the material so we have to convert this into meter cube. So weight of the material is total volume into density. Since the density is given into 2681 kg per meter cube, we are converting this into this volume into meter cube to get the direct value of the weight of the material in kilogram. Okay, so by multiplying the total volume and density, we get the weight of the material as 0.198 kilogram. So now the material cost will be weight into cost per unit, that is equal to rupees 19.8. To help with more complex geometries, engineers use standardized reference tables like the ones on the slide. Table A provides densities of common industrial materials such as mild steel at 7.868 gram per centimeter cube, cast iron 7.2 gram per centimeter cube, and next table, this outlines standard geometric formulas for calculating the areas of the plane figures, including squares, triangles, right angle triangles and parallelograms, which are essential for finding cross-sectional values before computing the volume. So the next reference table is to calculate the volume of solid. Similarly, these reference charts provide formulas for calculating the volumes and surface areas of the regular solids. So whether you are dealing with a standard regular rectangular solid, a cylindrical or hexagonal prism, a regular pyramid or frustum or a sphere, breaking down complex component into these fundamental shapes is the key to accurate industrial cost estimation. Now we will proceed with the second example, H-shaped slide block, which is shown in the figure. So let's work through a more complex example, that is calculating the material cost of a H-shaped slide block shown here. We are given a material density as 7.2 gram per cc and 1 kg of the material cost 6.25 rupees 6.25. To solve this efficiently without missing internal details, we break the block down into positive and negative volumes. So volume of A, volume of B, volume of C, volume of D, and volume of E and volume of F is calculated as in the previous similar to that of the previous problem. And finally we have to sum up all the volumes. Here we are summing off all the volume of A, volume of B, volume of C and volume of D and volume of E, and subtracting the volume of F because it is a through hole. Okay, it is of 65 diameter, it's a through hole. So we are subtracting from the total volume of the block, the volume of F is subtracted. Finally we will get the total volume as 7392663.16 millimeter cube. Then to find out the weight of the block, as we did in the previous problem, it's a total volume into density, which gives an answer as 53.225 kilogram. So total material cost will be weight into cost per unit weight. So we will get 332.66 rupees. So next we will go into another example which shows a mass producing tapered shafts. So we need to estimate the total weight and material cost to manufacture a batch of 220 pieces of the step tapered shaft shown in the diagram. The shafts are made up of mild steel with a density of 7.87 gram per centimeter cube, and the unit cost as rupees 100 per kg. So we have to calculate the material cost for 220 such shafts. Here section B is a frustum of cone, meaning we must apply the frustum volume formula, that is h by 3 into A1 plus A2 plus root of A1 plus A2. Make a correction here, A1 h by 3 into A1 plus A2 plus root of A1 A2. If we apply the area of 1, area of 2, and if you apply the values of area of A1 A2, we will get the volume of B as 10,775.675 millimeter cube. Okay, here the section E contains a negative internal bore with a 10 mm diameter, which must be subtracted from the outer 14 mm diameter section. So the formula becomes pi by 4 d square minus d square into L. Adding the volumes of section A, B, C and D and accounting for the hollow bore in section E gives a single shaft volume as 35647.265 millimeter cube. Multiplying by the density of 7.87 into 10 power minus 6 gives a single unit weight of 0.2805 kilogram. Since we are manufacturing a batch of 220 pieces, the total material required is 61.72 kg. So the total raw material cost for the entire batch comes out to rupees 6,172. I think it is clear for you. Now we will move on to the next example, a bush. Okay, bush with a process losses. So let us work through this problem. We need to calculate the material cost of 20 gunmetal bushes based on the technical drawing provided. The material density is 8.3 gram per cc. The unit cost is rupees 350 per kg, and we must factor in a 10% material loss due to scrap generated during the machining process. So note the dimensions are all given in centimeter. Okay, so in the diagram it is given as all the dimensions are given in centimeter. So we will keep our volume calculations into cubic centimeters to align with our density units. The net volume is calculated by adding the volumes of all the outer flanges and subtracting the central step internal bore. Okay, finally considering 10% material loss, okay, so total weight of the material will be 43.34 and the material cost will be rupees 15169. Now we will move on to the another example, the loss allocation. So complex machine part, this is a complex machine part. Let's conclude with our the final problem of complex machine part, estimating the material cost for the complex flanged machine part. The material density is given as 8.2 gram per centimeter cube. The density of the material is 8.2 gram per centimeter cube and the cost of the material is 30 per kg. Assume 20% wastage of the material of the finished component and totally 6 holes for the bolt. So to find the net volume, we take the solid outer envelope volume and subtract the central stepped bore sections B and C and the corner relief profiles F and the volumes of the 6 bolt holes which are represented by section D and E. Following this approach, the net volume of the finished component is 480,543.54 millimeter cube. Next we calculate our 20% machining wastage allowance, which adds an extra 890.59 millimeter cube. So total gross volume of the machine part will be, summing up these two, will get 480,543.54 millimeter cube. Multiplying this gross volume by our material density, which gives a total raw material weight of 3.94 kilogram. So at a rate of rupees 30 per kg, the final material cost will be 118.20 rupees. So with this we are concluding our analysis of cost elements and material estimation. So thank you very much for your time, and I look forward to seeing you all in our next session. Thank you very much.